Hi, my name is Gary Hawkins, and this video is on exploring photometry. So, by way of introduction, I'm going to assume that you are familiar with the concepts and terms relating to photometry. This video is not about what photometry is, it's about how you undertake photometry and photometric analysis. I'll begin with a few opening remarks and a brief introduction to the equipment and software that I use for photometry. We will then step through the collection of data for a variable star using my measurement equipment. And finally, we will walk through the post-processing and basic analysis of this data. My primary goal of this video is to show you that photometric measurements are well within the grasp of the average amateur astronomer. I've been doing astronomy for about 4 years. I started doing visual astronomy with a very basic push dot, an Orion XT8, that we took out into the desert while we were camping. My interest in astronomy rapidly progressed into electronically assisted astronomy, more commonly known as EAA, to combat the light pollution that I had at my home location at that time, which was in the northern part of the city of San Diego in California. And also, EAA was an ideal platform to undertake public outreach, which I did through the San Diego Astronomy Association. With the onset of COVID, face-to-face outreach became impractical, and so then I went online with an SDAA colleague to do EAA live streaming, primarily through YouTube. An exoplanet course earlier this year made me realize that my EAA rig was actually also extremely suitable for photometry and for the use within citizen science projects. As eclipsing binaries are much easier targets than exoplanets, that's where I started. I'm a member of the San Diego Astronomy Association, and in particular, I take part in the Outreach Special Interest Group. I also work closely with the Boyce Astro Foundation, which is where I did my exoplanet course, and timeanddate.com, where we primarily do live streaming associated around lunar eclipses. My EAA photometry setup is a fairly cheap and cheerful setup. It's based around a 1988 Celestron CH Schmidt-Cassegrain telescope. Most of my gear is secondhand, and this particular OTA in this particular configuration has a field of view 30 arc minutes by 30 arc minutes. I had to make very few hardware changes to my EAA setup to make it suitable for photometry. And the primary one was the replacement of the light pollution filter that I was using for EAA with a UV-IR cut filter to constrain the response of the 533 MC color CMOS camera that I was using to a spectral range between 400 to 700 nanometers. My EAA software setup is shown in blue, and it's based around SharpCat Pro, which is one of several extremely well-known packages used for electronically assisted astronomy. My mount is a EQ6R by Skywatcher, and so I use the EQ Mod EQ Tour software, which is a public domain software to control the mount. I use the Cart to Seal SkyMap, and for guiding, I use the very popular PhD2 software suite. For EAA live streaming, I use OBS Studio, which usually goes out to YouTube. In order to do photometry, I need to basically add just two pieces of software. The first of those is AIJ, which is the software tool that I use to do differential photometry. And the second tool is a tool called Dimension 4 that ensures that my PC clock is always synchronized to the time standards that are widely available on the World Wide Web. So I have accurate time measurements, and accurate time measurements are critical for photometric measurement. All of the programs that I'm using are open source, except for SharpCat Pro. Other tools that I use while doing photometry include those available through the AAVSO. In particular, I use the Variable Star Index, VSX, and the Pick a Star portal. I strongly recommend, if you're interested in photometry, that you become a member of the AAVSO. This allows you to submit results through the WebOps application. And perhaps most importantly, it also allows you to get an AAVSO mentor. And I found that my mentor has been particularly helpful in helping me develop my photometry skills. In addition to the tools available at the AAVSO, I also use the Aladdin Sky Atlas, along with another program called StarAlt that shows me the elevation of my target star on my observing evening. And one of the reasons you want to know that is simply because you don't really want to be doing photometric measurements below about 30 degrees in elevation. The other thing I would say about photometry is don't be afraid of your location. Even if you're located in heavily light polluted skies, it is possible to actually do some good photometric measurements. And I have done photometric measurements from my old QTH, which is indicated by the red arrow, my current home location, which is indicated by the orange arrow. And I've also done photometric measurements from the San Diego Astronomy Association dark sky site towards the Mexican border, indicated by the blue arrow. The majority of my measurements have actually been done at the old home location in Boreal 8 skies. So don't be afraid of your location. You'll be able to get good photometric measurements as long as you follow the correct procedures. I think with photometry, I think the key thing is workflow. I think it's if you define a workflow that works for you and you consistently use that workflow, you're going to have success because you will do everything the same every time that you do it. I actually use the sequence function within SharpCat Pro to walk me through the acquisition, post-processing, and differential photometry process. But you could just as easily use a spreadsheet. You'll find that your equipment has an operational sweet spot. I mentioned the field of view of my equipment earlier on, 30 arc minutes by 30 arc minutes. This gives me an operational sweet spot of 10th to 13th magnitude targets with exposures in the range of about 20 to 60 seconds. You don't want to go below 20 seconds as you will see scintillation effects in your results. And if you go much above 60 seconds, your guiding's got to be working fairly well. I do all of my image acquisition using SharpCap. I do my post-processing using the ASTAP tool that I mentioned earlier on. I use this for both plate solving that ensures that each image has its WCS coordinates placed in its FITS header. And I also use ASTAP to extract either the red, green, or blue channel for photometric analysis. I typically extract the green channel since this will give you results that approximate very closely to using a Johnson V filter with a monochrome CMOS or CCD camera. And I do all my photometric analysis using the tool Astro Image J. which was initially designed for exoplanets, but is a very good tool for standard differential photometry. So, in a few moments, we're going to look at the measurement and analysis of the variable star V576 PEG. This variable star is in the constellation of Pegasus. It's a eclipsing binary type EW spectral class K4, and it has a magnitude range of between 11.2 to 11.8. This has a fairly quick period of about 0.26 days, just over 6 hours. So in several evenings, you can get the complete light curve for this particular variable. On the right-hand side of the image here, you see a finder chart that was obtained from the AAVSO. The target star is in the center. One of the interesting things is that the AAVSO only identified one comparison star within the field of view of my telescope. This is going to be a problem for differential photometry for two reasons. One, the identified comparison star is two to three orders of magnitude less than the target star. And secondly, you need more than one comparison star ideally. So we're going to be randomly selecting comparison stars, as you'll see in the later part of this video. This is my target star viewed in the Aladdin light package. The star is in the center of the display there. And you'll see within Aladdin, it's actually identified by its more typical designator RXJ2311.0 plus 2142.